Welcome to this custom deep dive. Today's mission is exploring FlyingBytesPro. Now, if you have ever programmed a classic AVR microcontroller, well, you probably know the exact feeling.
Oh, absolutely.
It is like popping the hood of an old car and just finding this tangled, greasy mess of wires. You are just sweating, hoping you don't cross a connection, miscalculate a hex value, and accidentally brick the chip.
Right, which is basically the worst case scenario.
Yeah, exactly. But today, we're looking at a tool that is basically like popping that same hood, but finding a perfectly organized, clearly labeled engine bay instead.
Which, I mean, let's be honest, is a really rare feeling in hardware programming. And the reason it can actually offer that level of organization really comes down to its architecture.
Right, because it is strictly not just a graphical wrapper around AVRDUDE, like a lot of other software does.
Exactly. Instead of doing that, FlyingBytesPro actually uses its own direct native USBasp programming backend, built completely around libusb.
Okay, so let's clarify why building that from scratch actually matters mechanically. By skipping that middleman, I mean, it isn't just sending requests into some black box.
Right. It is talking directly to the programmer hardware. So it manages the flash memory and the lock bits internally, which gives the software total control.
And total control unlocks smart automation, right?
Yeah, that direct control really powers the task screen. It lets you build this custom one-click sequence. You tell it to erase the chip, set the pre-write fuses, program the flash, verify, and lock it down.
And it just runs that whole sequence automatically.
Yep, all in one go.
Wait, hold on, though. Let's unpack this for a second. If we are taking this incredibly complex sequence, boiling it down to a single click, and automating it, aren't we just hiding the complexity again?
I mean,
Well, if something breaks, putting a cheap plastic cover over the engine bay means I won't know why it failed.
you would think so, but that is where the dual log system kicks in. It is not really hiding the engine, it is giving you a dashboard.
Oh, okay. How does that work in practice?
So during a normal workflow, the mini log gives you a concise, one-line summary per cycle that keeps you from drowning in all that USB traffic data.
Which is great until something actually goes wrong.
Exactly.
Yeah.
But the second something goes wrong and you need to debug, you just click over to the full log. And there you see every raw ISP command and USB control request happening under the hood.
Okay, so just organizing the complexity, not burying it. If you need the raw data, it is literally right there.
Yeah, and you see that exact same philosophy in how it handles the microcontroller's memory. It actually treats the flash and EEPROM as live, editable, hexadecimal memory views.
And it is pretty smart about it, too. Like, if you are using a sparse HEX file, it actually tracks which bytes are defined, so it doesn't just blindly write undefined memory.
Right, which ties perfectly into the Smart Read feature, because if you were reading the flash memory, the software just reads from the beginning and stops at the very first completely erased page.
Wow, that must save a ton of time.
It really does. But if you suspect a bootloader is hiding in the upper memory, you just use full MCU read to force it to scan the entire address space.
Okay, here is where it gets really interesting for me. It is like having a translator who doesn't just read the menu to you, but explains exactly how the dish is cooked. The fuse decoder.
Oh man, yeah. If you have ever spent 3 hours trying to unbrick a chip because of a bad hex value for a fuse byte, you will appreciate this.
Right. It translates those raw hex bytes into readable options across 8 different languages.
Yeah, it takes the math out of it.
Yeah.
But it still lets you see the exact technical identifier you are flipping, like CKSEL.
But translating those fuses is really only half the battle, right? Because this granular control has to extend directly into the physical hardware's limitations.
Exactly. Once the software knows what you want, it has to force the physical hardware to accept those instructions. And that gets messy. It has to map out the unique memory architectures for over 170 different chips.
So it has to know exactly how a tiny 6-pin TPI chip differs from a standard SPI device, down to the exact EEPROM page geometries.
Yes, it really has to respect the physical reality of the hardware, which brings us to the SCK clock selector.
Oh, right. Because the software talks directly to the hardware, you can manually choke the programming speed down to just a few hundred hertz.
Which is an absolute lifesaver. High-speed USB transfers are great for reliable setups, but if you have an old chip running on a sluggish intern clock, hitting it with high-speed data is like trying to force-feed it from a fire hose.
It will just fail, yeah.
Right. So throttling that speed gives the target, maybe one recovering from a bad fuse change, time to breathe and accept the data. Plus, there is a command line interface using that exact same backend for batch scripting.
So what does this all mean for the philosophy of classic AVR development? It seems like it combines a task runner, memory editor, fuse decoder, and diagnostic tool into one workflow.
Yeah, it perfectly embodies the classic AVR ethos. It doesn't try to hide the microcontroller from you, it just makes working with it better and more understandable.
Why on earth would there be an option to intentionally throttle the programming speed down to a few kilohertz or even a few hundred hertz? That sounds agonizingly slow.
It does sound completely counterintuitive in a speed-obsessed world, I'll give you that. But if we connect this to the bigger picture, hardware recovery isn't about speed. It is entirely about stability.
Okay, walk me through that.
Let's say you have a brand new microcontroller fresh from the factory. Many of these chips ship with an internal oscillator enabled, paired with a divide by 8 clock prescaler,
Meaning?
meaning the chip is running internally at a tiny fraction of a megahertz.
Mm.
If your programmer attempts to blast data at it at a high clock speed, the chip physically cannot process the electrical signals fast enough to hear them. It is effectively deaf to the programmer.
Oh, so you have to intentionally slow your programmer down to match the incredibly slow speed at which the chip is currently capable of listening.
Precisely. Old hardware, unusual low-power clock configurations, or targets that are recovering from a botched fuse change, they require incredibly slow communication just to get back on their feet.
That makes so much sense.
The tool is deliberately designed to handle those fragile edge cases. It doesn't assume every piece of silicon on your desk is running at maximum efficiency.
It's careful when it needs to be. But when you're running a fast clock, it also verifies intelligently. Earlier, we talked about sparse firmware files with all that undefined empty space.
Right?
When the software runs a verification pass, it only checks the bytes that are actually defined in your hex file. It doesn't waste time verifying empty space. And if you need an absolute guarantee, it summarizes the contents with a CRC16 checksum.
Which is basically a mathematical fingerprint of your data. The software adds up the data in a specific way to generate a shortcode, and you can compare that code against your original file to prove that not a single bit was corrupted.
So we have a tool meticulously attuned to the individual physical reality of the chip sitting on your desk. But what happens when you need to scale up?
Like for production.
Yeah, let's say you aren't just flashing one chip on a breadboard. You are programming 50 of them for a small production run. Or you need to share your exact setup with a manufacturer overseas.
Well, that requirement is handled by the project system.
Right. You can save your entire environment as a portable FlyingBytesPro project file. It bundles the device, the clock, flash and EEPROM images, fuse settings, locks, and your automated task sequence into a single file.
You hand that file to a colleague, and they don't have to meticulously rebuild the setup.
Which makes perfect sense. But then I saw this other detail in the manual, and it completely threw me. They included a separate command line interface, the FlyingBytesPro CLI.
Ah, yes, the CLI.
Wait, hold on. They spent all this time building this gorgeous, localized, breathing visual interface just to include a command line terminal tool anyway? Doesn't that completely defeat the purpose of avoiding wrappers?
I can see why it seems contradictory at first glance. But it's actually the ultimate expression of scaling a workflow. The CLI isn't a wrapper around the GLI, and the GLI isn't a wrapper around the CLI.
Okay.
There are simply two doors into the exact same architecture. The CLI uses the exact same direct libusb backend we discussed earlier.
Oh, so they share the exact same engine under the hood.
Exactly. The CLI utilizes an AVRDUDE style command structure, which makes it perfect for writing automated scripts or batch files.
So you get the visual tools to understand the chip.
And the command line tools to scale your production once you know exactly what payload needs to be written.
Wow. So what does this all mean when we step back? The real magic of FlyingBytesPro isn't just one isolated feature. It's not just the native backend or the fuse decoder or the sparse hex handling. It's how seamlessly they all connect.
It really is an ecosystem. The chosen microcontroller dictates the memory boundaries. The fuse decoder explains the bootloader configuration.
The visual flash view shows you exactly where that bootloader lives. The task sequence automates the execution, and the logs report the unvarnished electrical truth when you need to debug.
It refuses to hide the microcontroller from you and instead tries to make working with it better.
For you listening, whether you are a hardware veteran who's been writing C code for classic chips for 20 years, or a curious learner just trying to blink your first LED without destroying your hardware, there is immense value here. Tools that treat you as intelligent, capable, and deserving of absolute transparency are so rare.
It doesn't try to protect you with opacity. It just gives you the tools to understand.
And that philosophy leaves us with, I think, an important final thought.
Yeah, something to mull over. If the tools we use profoundly shape how we think about the materials we work with, how much more innovative could modern software development be if all our daily tools stripped away their opaque wrappers?
What if they stopped trying to protect us from the hardware and finally let us see the raw mechanics underneath?
Imagine getting back to that pure satisfaction, knowing exactly what is happening inside the device. No magic, no hidden layers, just you, the silicon, and the physics.